In this video, I'm going to introduce you to the formula that we use to calculate the speed of a wave propagating along a stretched string. However, before we can get to that formula, I need to introduce you to the idea of the linear mass density. The linear mass density is denoted by the Greek letter mu. It is defined as the ratio of the mass of a segment of string to the length of that segment. Let's do a quick video to illustrate the use of the formula. Let's say we have a segment of string with a length of 5 centimeters. Let's say that this segment of string has a linear mass density of 0.03 grams per centimeter. And let's say that we want to find the mass of the segment. This isn't a super hard calculation, but I would still encourage you to pause the video, try that on your own, and then rejoin the video. Okay, starting from the definition of linear mass density, I can solve for mass. So I have then that mass is equal to linear mass density times length. So I just substitute. The linear mass density would be 0.03 grams per centimeter. The length would be 5 centimeters. Centimeters cancels against centimeters. So we have that the mass of that segment is 0.15 grams. Okay, so now I have introduced you to the idea of linear mass density. We did an example problem with it. Now that I've introduced you to the linear mass density, we are ready to see the formula which is used to calculate the speed of a wave propagating on a stretched string. So here we go. Let's say this is a string, and there is a little wave disturbance propagating down the string at speed c. Let's say that the tension in the string is capital T, the linear mass density is mu. Then the speed at which that wave propagates down the string is the square root of the tension in the string divided by the linear mass density. Now that I've shown you the formula for the speed of a wave on a stretched string, we're going to do a quick example problem to practice using this formula. In this example problem, I have a string. One end of the string is attached to the wall. Then the string runs over a pulley and then goes down to a mass, capital M. The length of the segment between the wall and the pulley is 50 centimeters. That mass hanging from the string is 500 grams, and the linear mass density of the string is given. It is 3.8 times 10 to the minus 3 grams per centimeter. So we want to find the speed at which a wave propagates on the string. And then we want to use that result to figure out how much time would be necessary for a wave pulse to start at the wall and then propagate to the pulley. These are both straightforward calculations, so I would encourage you to pause the video here and then try all of this on your own and then rejoin the video. To solve part A, all we need to do is substitute into the formula here. We have that wave speed is the square root of the tension divided by the linear mass density. Now, the tension in the string would be exactly what was needed to support the mass here. So we can say that the tension in the string is the weight of the hanging mass. So then tension becomes big M times little g, and then divide by the linear mass density. So let's make our substitutions. I'm going to do this calculation in CGS units. So I'll put the mass in as 500 grams. I'm going to put in little g as 980 centimeters per second squared. The linear mass density would be 3.8 times 10 to the minus 3 grams per centimeter. Plugging this into my calculator and rounding off to 3 significant digits, I get 1.14 times 10 to the 4. Now let's check the units. Grams cancels grams. And if you look at what remains, we have centimeters per second squared in the numerator, 1 over centimeters in the denominator. So 1 over centimeters in the denominator flips up into the numerator. So we end up with centimeters squared over second squared in the numerator. And when we take the square root of this, we get as our final unit centimeters per second, as we would expect for a speed. So a wave created in this string would propagate along the string at 1.14 times 10 to the 4 centimeters per second. Part B of the problem asks us how much time would be needed for a wave pulse which starts at the wall to propagate over to the position of the pulley. Let's use the symbol L to denote that 50 centimeter distance. To get the time it would take a pulse to travel from the wall over to the pulley, we can use our standard formula for motion at a fixed speed. Specifically, for something moving at a fixed speed, we can say that that speed is equal to the distance traveled divided by the time it takes to travel that distance. In this problem, the speed we're talking about is the wave speed, which we're calling lowercase c. The distance that the signal has to propagate, we're calling capital L for 50 centimeters. And let's call the time that it takes to travel that distance delta t. So rearranging this a bit, let's bring delta t up to the numerator, bring c down to the denominator. We then get delta t equals L over c. So substituting, L would be 50 centimeters. C would be 1.14 times 10 to the 4 centimeters per second. Putting this into my calculator, I get 4.40 times 10 to the minus 3. And I will leave it as an exercise to calculate that the unit turns out to be seconds. So in this video, I have introduced you to the idea of linear mass density. I've introduced you to the formula that we use to calculate the speed of a wave propagating on a stretched string, and we have done a simple example problem using all of this. In the next few videos, we're going to be exploring the idea of wave interference and seeing how that leads to the phenomenon of a standing wave.